The Michaelis-Menten equation can be algebraically transformed into more convenient forms, convenient in terms of plotting experimental data. So the first of this, which is actually the most popular transformation of the Michaelis-Menten equation, is the Lineweaver-Burk or the double reciprocal plot. So starting from our Michaelis-Menten equation, we get the reciprocal of the two sides of the equation. So we have 1 over initial velocity equals S over V max times S plus Km over V max times S. So simplifying this, we can cancel out S in this term, and doing some rearrangements, then we have 1 over initial velocity equals Km over V max times 1 over the substrate concentration plus 1 over V max. And we get the slope-intercept form of a line. So our y is the inverse of the initial velocity. Our slope is Km divided by Vmax. Our x is the inverse of the substrate concentration, and our y-intercept is the inverse of Vmax. So for this one, what we plot on the x-axis is the inverse of the substrate concentration. On the y-axis, we have the inverse of the initial velocity, and we will get a straight line. So the slope of this line, again, the slope is equal to Km over Vmax. And we have the y-intercept, which is equal to 1 over Vmax. And actually, the x-intercept of this equation is equal to negative 1 over Km. So instead of dealing with the hyperbolic graph, this linear form of your Michaelis-Menten equation is more convenient. So let's try using this Lineweaver-Burk equation on some data. So we are given the concentration of the substrate in millimolar and the initial velocity in micromolar per second. So we can create a table, and I have here the inverse of the substrate concentration. And prior to getting the inverse of the initial velocity, I change the unit of my initial velocity so that the units are consistent. So from micromolar per second, I converted it to millimolar per second and proceeded to plotting 1 over S on the x-axis and 1 over initial velocity on the y-axis. So we have the slope and the y-intercept. So again, the slope of our plot is equal to 301.67, and this is equal to Km over Vmax. And our y-intercept, which is equal to 98.665, is equal to 1 over Vmax. So we can get the value of Vmax from the y-intercept. So get the reciprocal of the y-intercept, and you will get a value of 0.0101. The units are millimolar per second. And now that we have the value of the Vmax, we can plug it here and get the value for the Michaelis-Menten constant. You will get a value of 3.058 millimolar. So this is how you use your Lineweaver-Burke equation for kinetics data of your enzymes. Aside from the Lineweaver-Burke equation, we also have another transformation of the Michaelis-Menten equation. It's called the Edey-Hofstee plot. The Edey-Hofstee plot is derived by, so again, starting from our Michaelis-Menten equation, so we cross-multiply this. So we have initial velocity times substrate concentration times initial velocity plus initial velocity times Km equals Vmax times substrate concentration. Then you divide this by S, and you have V naught plus V naught Km over S equals Vmax. So rearranging this, we have initial velocity equals negative Km times initial velocity over substrate concentration plus Vmax, which is again an equation of a line in the slope-intercept form. So we have initial velocity as our y, negative Km as our slope, initial velocity divided by substrate concentration as our x, and Vmax as our y-intercept. So if we plot this, we plot initial velocity over substrate concentration on the x-axis and initial velocity on the y-axis. You will get a line with a negative slope. So again, your slope is equal to negative Km, and your y-intercept is equal to Vmax. Now, you might think that the Edey-Hofstee plot is more direct because unlike your Lineweaver-Burke, wherein you're getting the reciprocals, this one will give you the maximum initial velocity directly, and likewise your Michaelis-Menten constant. However, notice that you have dependent variable on both axes. So on the x-axis, we plot a value using the value of a dependent variable, which is the initial velocity. So we now have errors both on the y-axis and on the x-axis, which is different with the Lineweaver-Burke equation because in there, you have the reciprocal of the substrate concentration on the x-axis, and that is not a dependent variable. So your substrate concentration is an independent variable. Let's try using the Edey-Hofstee equation to the same data that we solved. This time, we have initial velocity divided by substrate on the x-axis and initial velocity on the y-axis. So we notice some difference. The Km, or the Michaelis-Menten constant, is again equal to negative of the slope. So the slope is negative 3.091. So our Michaelis-Menten constant is equal to 3.091 millimolar. And our y-intercept is equal to Vmax. So Vmax is equal to 0.0102 millimolar per second. So we see some differences in the two parameters with those obtained using the Michaelis-Menten Lineweaver-Burke equation. So again, the Lineweaver-Burke equation is more accurate than the Ebbe-Hofstee equation.